Hello everyone, my name is Jonáš Kulhánek and I would like to present you our work titled Tetra-NeRF representing neural radiance fields using Tetrahedra. In the Tetra-NeRF paper we propose an alternative way to represent radiance field for volumetric rendering. The ultimate goal is to have a compact representation which naturally offers better resolution closer to surfaces. Currently there are several different ways to represent the radiance field. NeRF paper used MLPs which offer good reconstruction quality but are slow to train. An alternative is to construct a sparse voxel field as in planoxels, or one can use a hash grid with an MLP on top to resolve collisions as in INGP. However, these methods are not aligned to scene and may waste representation capabilities in regions where coarser representation would be sufficient. Finally, there were point-based representation, but the problem is that they only represent radiance field in close proximity to the 3D points. In our representation, we also store features in a point cloud. However, our representation is continuous and there are no holes, similar to grid-based or MLP methods. We initialize our representation with the input point cloud. In the paper, we consider the ColMap SFM point cloud, as ColMap is often used to obtain the camera poses for reconstruction, and therefore points are available without any additional costs. We associate each point with a trainable vector. Next, we run the Delaunay triangulation to obtain a tetrahedral mesh. This mesh is a set of non-overlapping tetrahedra whose union is the convex hull of the original points. We then use these tetrahedra as our field representation. When rendering a single ray, we first sample points along the ray as in NeRF. These points are sampled between the first and last intersection with the tetrahedra. For each sampled point, we find the tetrahedron in which it is located. We compute its barycentric coordinates and interpolate 4 feature vectors stored at the vertices of the tetrahedron. Now, in order to find the tetrahedra of the sampled points efficiently, we march along the ray through the tetrahedra. We use traditional ray tracing to find triangular intersection of the ray with all the tetrahedra faces. We split the ray into intervals and we find to which interval each sampled point belongs. We then construct the point's barycentric coordinates from the triangle barycentric coordinates. The resulting features are then passed through a shallow MLP to obtain the density, and after adding the viewing directions encoded as Fourier features and passing it through a second shallow MLP, the color is obtained. Given this set of densities, we perform a biased fine sampling where we sample according to the PDF obtained from the first set of samples as in NeRF. Finally, we combine both coarse and fine samples and perform volume rendering to obtain final color. Here, you can see how the radiance field is optimized during training. In this reconstruction, we use the sparse ColMap model. Here, we also show the training process for dense ColMap reconstruction. Let's compare Tetra-NeRF to voxel grid-based representation that use trilinear interpolation. The trilinear interpolation takes the 8 feature vectors stored at voxel corners and interpolates between them. This interpolation, however, is cubic along the ray. On the other hand, barycentric interpolation only takes 4 vectors stored at the tetrahedron vertices and is linear along the ray. Since the input points will be located in proximity to surfaces, Tetra-NeRF's representation naturally puts smaller tetrahedra close to surface. You can see this when we compare it with dense grids where the resolution is uniformly distributed. As you can see, our approach offers much better resolution with the same memory requirements. Here we show the reconstructions on the MIPNeRF 360 dataset. To summarize, we have presented an alternative radiance field representation, which is based on the Delaunay triangulation of the input point cloud. The representation naturally offers more resolution close to surfaces and achieves state-of-the-art results. Our source code is publicly available and integrated with NeRF Studio. Please visit us at our poster on Friday at 10:30.